So we'll be starting the last topic of the course, which we are supposed to cover in the data structures and algorithms course. And if you recall, I skipped these 3 lectures. Basically it's one topic, that is the B trees, right? So we will be starting this topic now. Although these are 3 lectures, I will try to cover these in 2 videos, but maybe this third one contains the deletion of nodes in the B trees, which is a bit complex, so it may end up being covered in 3 lectures instead. Let's see what happens. So let's start with the topic of B trees. So the motivation of B trees is based upon the problem that we cannot fit each and every item in the RAM, or each and every data which is available with us. Not every data, not every type of the data can be stored in RAM. We need to store some of the data in the hard drive, right, in the hard disk. But the problem here is that since the fabrication technology of the RAM is electronic and the fabrication technology of this hard disk is mechanical, so obviously this one is going to be fast, this RAM, as compared to the hard drive, right? So when we plan to store something in the hard drive, we need to opt for the best suited data structure which works very well and is customized to work for better in case of the data is stored in the hard drive, right, instead of RAM. So to quantify the comparison between the RAM and the hard disk, the time which is required to perform one input output operation on the hard drive, during that time we can perform 2 lakh instructions in the RAM, approximately, right? It's not exactly like this, but it is an approximation, which is a huge amount. So it shows the slow performance of the hard drive, right? So based upon this motivation, the goal here is to devise a tree which is a multi-way search tree, right? So far you have covered binary trees, you have covered binary search trees, you have read about AVL trees, right? Where we used to have a node and the node had 2 children, right? And the 2 children may had multiple children further, right? But the in B trees we will have more than 2 children for a node, and within each node we may also have more than 1 keys as well, right? So so it is a generalization. The B tree is a generalization of a binary search tree, right? Where each node has at most has at most m children, right? Where m is a predefined number, which I'll be talking about shortly, right? Now if k, which is any number, again a different number, which is less than or equal to m, is the number of children, then the node has exactly k minus 1 keys, right? For example, there is a node, right, and this node has, let's say, 1 child, 2 child and 3 children, right? If you see here, now since it has 3, this node has 3 children, it means this will have 3 minus 1 number of keys within it, right? So maybe the first key may be A, the second key may be, let's say, D, and the third key may be, let's say, Z, right? Maybe. So this is the concept here, that the whatsoever is the number of keys in the parent node, number of keys plus 1. For example, this node has let's say this key x, 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 these 3 keys. It means that it will have 3 plus 1 children. One child will be like here, one child will be here, one child will be here, one child will be here, right? If you see the other way around, the if a node has, let's say, if you see here, it has 4 children, so it will have 4 minus 1 keys in the node, right? And the keys and the tree is basically ordered. It is just like binary search tree, it follows an order. Like if you see here, this is k1 which may be having a value, let's say 8, and this is k2 which may have value, let's say 10. This is k3 which may have value 20. This may be like 24, and this may be like 80, right? So within this is a parent node, right? This is a parent node. Now the keys which are less than 8, for example 5, 6, 2, whatever, so they will be in this child, right? And the keys which are between 8 and 10, for example 8.5, 8.7, 9, those keys will be placed here in this child. So this is a multi-way search tree where keys are in a particular order. Now since I have not shown you the complete tree, so it may be a bit confusing for you, but wait for a while and I will try to construct a binary search, sorry, a B tree from scratch, and then you will be able to understand it. But these are a few properties of the B tree. Then okay, let me read it out so that I may not miss any point. A B tree of order m is a m-way search tree. Like a binary search tree is a two-way search tree, and a B tree of m order is a m-way search tree. B trees are balanced search trees designed to work well on direct access secondary storage devices. And when we say that the B trees are balanced, it means that all leaves of the B tree are on the same level. For example, this is a binary search tree. If you see here, here this can be drawn like this, where these two leaves and this leaf are at different level. But in a B tree, all leaves of the B tree will be at the same level. They will have same height. So that is why the B trees are always balanced, right? But how they become balanced, I will be telling you shortly about that. Now here, this is an example of a B tree, and again it is not constructed from scratch, but to give you a visual example of a B tree. Now if you see here, everything is in order. Now if you notice m, the values which are greater than m, right, like n, o, p, q, r, s, t, whatever, so they are on the right side of m, right? And the values which are less than m, like a, b, c, d, although a is not stored here, but I was giving just an example, they are on the left side of m. Now again, considering this node, the values which are less than d, like a, b, c, they are on the left side. The values which are greater than d and are less than h, they are between a node which lies between these two values. Now how it gets created, I will be telling you shortly. I am repeatedly saying that just to make sure that you get to keep you engaged here. But these are the properties. Now again, if you see here, this data is stored in a binary search tree, and the height of the binary search tree here is 5, right? If we store the same data in a B tree, the same data is stored here with the height of 3, right? So the less the height of a tree, whether it be a binary tree, binary search tree, AVL tree, or B tree, the better the tree is, because you will have to traverse lesser number of levels to reach the leaves. Like if in the worst case you have to go through 5 levels, but in this case, in the worst case, you have to go to 3 levels. So it is the B tree is better. But again, there is a catch that here, if you see here, within each node in the binary tree or binary search tree, we have one key, but in the B tree, it's a bit complex. Each node has more than one keys, and at times one node can have 3 keys, the other one can have 2 keys, depending upon the value of a particular variable, which I'll be telling about in the properties section of the B tree, which is right now here. Now, a B tree is a rooted tree with its root having the following properties. One, every node in the tree will have following properties. For example, again, let me tell you a good news here before going into the details. We are not doing any code of this B tree, right? So its code will not be asked from you in any exam or any assignment for that matter, or any quiz. But of course, we will perform the insertion of keys in the B tree and deletion of keys in the B tree as well, right? So while I am telling you about these properties, so don't be tensed about or concerned about the coding. We are not covering its coding here. So in every node, there is a field which is called nx, which shows the total number of keys to be stored in a node. For example, in a B tree, this node, apparently it's big, this is a bit smaller, this is a bit smaller, so this is a bit smaller. So this node may contain x, y, z, t, for example, these number of keys. Now if you see here 1, 2, 3, 4, since this node has 4 keys, then it will have 4 plus 1, 5 children, right? 1, 2, 3, 4, and it will have 5 children, right? And then this node may contain 2 keys, this node may contain 1 key, this node may contain again 2 keys, this node may contain let's say 3 keys, and this node may contain. So every node, depending upon a particular variable, which I'll be telling you shortly, so every node keeps track of the number of keys which are stored in that particular node. And then the keys which are stored in the B tree are stored in an ascending or descending order. As you can see here, these are placed in a increasing order, right? And then there is a Boolean variable in each node, which tells us that if the node is a leaf node or it's a non-leaf node, right? For example, here in these nodes, that Boolean variable will be on, but in these nodes, because these are not leaves node, the variable will be off, right? So these are the variables which are stored in each node. Then if x is an internal node, by internal node, I mean that, for example, this is a node, this is a node, this is a node, this is node, and then this is a node. These are nodes connected. So now these are what? These are internal nodes, right? So if x is an internal node, it will contain nx, where we know that this variable represents the number of keys stored in the node. So that node will contain nx plus 1 pointers to its children, right? For example, if a node has if a node has 2 keys, so it means it will have 1, 2, and 3 pointers to its child node, right? And the leaf node contains no children, or it is obvious, no need of writing that. The keys are separated by a range of keys stored in each subtree, right? This point I've already told you visually, that these, if you see here, let me find it better, yes, rather this one was better. Now these keys, all keys which are between D and E are placed here, right? All keys which are between q and t are placed here. All values which lie between t and x are placed here, right? So this is the interpretation of this particular point, right? So, and each leaf has the same depth, which we can see here, that each leaf in a binary, sorry, I'm repeatedly misinterpreting it. In each leaf in the B tree has the same level, right? Okay, then yes, I've covered it. Each leaf has same depth, and then yes, this one is very important, right? This one is very important, that there are lower and upper bounds on the number of keys a node can contain, right? For example, if you want to create a B tree, we will be given a variable which we call t, and the value of t can be any number, but it should be greater than or equal to 2. For example, if I say t value is 3, now this t will determine the upper and the lower bound on the number of keys a node can contain, right? And now how can we determine that? That's quite easy. Now if you see here, for example, okay, for example, I say t is equal to 3, then a node must contain at least t minus 1 keys, and it can contain at maximum 2t minus 1 keys, right? Okay, let me do it for you. So the minimum number of keys, minimum number of keys can be t minus 1, which will be 3 minus 1, which is 2, right? And the maximum number of keys will be 2t, 3 multiplied by 2, 6, 6 minus 1, 5. So each node in the B tree will have at least minimum 2 keys, and it can have maximum how many keys? Maximum 5 keys. But there is an important point, that this lower bound is not applicable on the root node. क्योंकि पहली दफ़ा the first time you create a node, it will have 1 key at least, okay, which is less than this minimum bound, right? So the minimum bound is not applicable on the root node. On rest of all the nodes in the B tree, minimum and maximum bounds are applicable, right? Now the question is that when we keep on increasing the number of keys, for example, I put 1 key here, which is okay, this is the first node and it's the root node, no problem. It is less than this minimum, no problem. Then I put another key, okay, fine. I put another key, fine. I put another key, fine. I put another key, fine. Now for example, if I had to put another key, for example, here, but already this node contains 5 keys. Now there is no space in this node. So what will be the mechanism of further? So there is a process which is called splitting. That is on the next slide, but since I've created this example here, I'll be performing that process here. What we will do is we will split this node into half. Like this portion will become a new node, this portion will become new node, and this middle node and middle value which is there, it will go up. Now how this happen? Please observe this. What I do, I make 2 new nodes, and what I will do, this half I'll bring here, and this half I'll bring here, and this middle value, this goes up, which is here, and it becomes like this, right? So this is called splitting. Now once this splitting is performed, now I can insert a new node into this B tree. I will be simulating this using a number of keys shortly, so to give you an example how it works. But this was important to tell you that how the bound on the number of keys in a node is implemented, right? Now What is the maximum height of a B tree? It's a simple formula with n entries. The question is important because the maximum height of a B tree will determine the upper bound on the number of disk access, because in the B tree, if something is in the leaf node, you have to go down to the leaf, so it will result in the number of disk accesses. So this is a simple formula where height of the B tree is determined by n plus 1 by 2 log to the base t, where t is value which will be predetermined. So given an example where we have 2 million keys, 20 lakh keys, and the t like t is set to 100, it means it will have t minus 1 minimum keys in a node, and at maximum it can have 2t minus 1 keys, right? So minimum will be 99 and maximum will be 200 and minus 1, that is 199 keys. So if we using this, if we make a B tree, the height of the B tree will be only, no sorry, the height sorry, the maximum height of order of the B tree will be 3. But if we store the same data in a binary search tree, it will have the height of 20. So there is like 1 2 3 and versus 1 2 3 4 5 up to 20. So it shows the efficiency of the B tree, right? Okay, ये तो खत्म हो गया. चले, instead of stopping this here, let me, because I have to give you an example where we construct a B tree. So let me go to the next slide, next lecture rather. Okay, now these are the operations which can be performed on the binary, sorry, again I misinterpreted. It's B, it's not binary tree, it's B tree, right? So the operations which can be performed on B tree are searching a value in the B tree, creating a B tree, splitting a B tree, which I told you shortly, inserting a key in the B tree, and deletion. This deletion is quite complex, so I'll be covering it in a totally separate lecture, right? So searching in a B tree is similar to searching in a binary search tree, but in the binary search tree we have one value in each node. But here in B tree we have more than one values in the node, so we will be doing in the same manner, but we will be watching for each and every value in the B tree, right? So it's like that, and then the searching operation is performed in a log of, in the binary search tree case, here this t would have been 2, but in case of B tree it's t, which is determined differently for different type of B trees. Then the splitting operation, which I told you earlier, when the node became full. So in the splitting operation, what happens is that the middle value, if you see here, if you want to perform splitting here, now if suppose that this is a node which is full, now we want to split it. What we will do is that we will take this half, this will become new node, we will take this half, this will become new node, and this value will move up to the parent node, right? If you see here, now it will always be odd number of keys, right? This will always, when become a B tree node become full, it will always be odd number of keys, it will not be even number of keys, because of the virtue of the formula 2t minus 1. This minus 1, now this 2t makes a number even, and when you minus 1 from this, and it becomes odd. So by virtue of this formula, it is always certain that when the node is full, there will always be odd number of keys in the B tree, right? So instead what I do, let me consider an example here, and let us consider values. इसको font बड़ा कर लेते हैं, right? For example, I have value 5, value and 60 and 6 and 20 and 30, right? This is enough. And let's say we set t is equal to, okay, 2, right? And min will be 2t minus 1, which will be t minus sorry, min will be t minus 1, which is 1, and max will be 2t minus 1, 2 into 2 4 minus 1 3. This will be, now let us okay, let me paste it in a new example here. Okay, right, इसको बड़ा कर लेते हैं. Now let us try to make a B tree. Initially we pick this 5 and we make a parent node here. Now I place 5 here, right? 5 aa gaya. Then we pick 20. 20 is greater than 5. I can like paste comma here and I will put 20 here. Now 20 is also inserted. Now then I put 60 here. 60 भी आ गया. Now I have to put the next number, but already this node is full, so I'm going to split it. Now how am I going to split it? This 2 will go up. This will become a new node, and this 5 will become a separate node, and this 60 becomes a separate node, right? Now if you see here, the lower bound, which is 1 key, so that is already in each and every node. Now when I insert 8, now if just like a binary search tree, now we have to insert 8 in this B tree. Now if you see here, 8 is less than 20, so I will go to the left. Now in the left, this node is available and there is space available in this node as well. So what I will do, I will place the 8 in this node, but in a proper order. Like 8 is greater than 5, so I will be putting it after 5 here, right? So 8 is placed as well. Now 50, let us pick 50, and 50 is greater than 20, so I'll be going to, and remember the insertion here is always going from top to down, so insertion actually happens in the leaf node. Apparently it looks that I can place 50 here as well, which is fine, but no, we have, if there is a leaf node, so we have to go to the leaf. If there were a leaf node further down there, so we would have gone there as well. Now 50 is to be placed in this node, but we have to do it in a proper order. So 50 is smaller than 60, so it will be coming before the number 60. Now then we have to place 30. Now 30 is greater than 20, will come here, and in this node we have space available here, and 30 will come here, right? And let's assume that we had another value, for example, okay, like 80, right? Now we'll come here, and if you see here 20, 8 is greater than 20, we go to the right, but if you see here, this node is now full because it has 3 keys. Now what we'll do, we'll be splitting it. We'll be moving this up, this 50, and okay, let me instead do it. Now 20, this 50 will go up, 50 will come here, right? Now this becomes a new node. Okay, पता नहीं कैसे हो गया, चलें, this is a new node. Then if you see, this node will remain intact. It will remain on the left side of 20, which will have 5 and 6. Now this thing has gone up. Now this 30 will become new node. Now this 30, since it is between 20 and 50, so this new node of 30 will come here, right? And this 60 will come here in the order, right? Okay. Now then I pick 80, and if I see here 80 is greater than 20, I'll come here, and 80 is greater than 50 as well, so I'll come here. In this node we have got a slot, we'll place 80 here, right? So this is how the splitting is performed, and one day this particular node may become full as well. So then we'll be splitting it further, and it will create a new node, and this is how the insertion process in B trees is performed, right? So I think this is enough for this particular component, and in the next lecture we will be going with deletion in B trees.